7, rational functions and in behavior. Here we go. Jackson's going to read.
A rational function is simply the quotient fraction of two.
What do you think? Functions. There it is. 2 functions. Keep going.
Rational function y equals f of x over g of x, where f of x and g of x are both polynomials and g of x is not equal to 0.
All right, g of x cannot equal 0, and then we have some rational functions. All right, so we're going to talk about in behavior again. All right, so we've talked about in behavior a little bit, and we're going to continue talking about in behavior. So in behavior of a rational function is determined by the leading terms of its numerator and denominator. And what we mean by leading terms is like the highest degree is like the leading term. All right, and so let's look at case 1. If the leading terms have the same degree, then we do have a horizontal asymptote, and then we look at the coefficients of those. All right, so it's y equals the coefficients when we have the same powers. And case 2 is if the denominator wins. If the denominator wins, then we have a horizontal asymptote at y equals 0. So when the denominator has a higher degree, it wins, we get y equals 0. And then if the numerator wins, then the in behavior is going to be infinity or negative infinity. We're not going to have a horizontal asymptote. All right. And then Jackson, read our note. This is big. This is big.
The degree of the numerator is exactly 1 more than the degree of the denominator. Then f of x has a slant oblique asymptote.
Good. All right. So if the numerator is exactly 1 more than the denominator, we're going to have a slant, or also known as an oblique asymptote. All right. I found out that's new for you this year. All right. You guys didn't do those last year. You did do horizontal asymptotes last year. All right. So let's look at our examples. So we have these rational functions, and we need to figure out if it's horizontal, slant, or neither. All right. So let's look at part A. So when I talk about an in behavior model, what is my leading term on my numerator in part A? So we look at the numerator, and 3x squared is going to overpower the 4x and the negative 7. We don't care about the 4x and negative 7. We care about the 3x squared. And what do we care about on the denominator? This 5x squared. And so that's like your in behavior model. It's 3x squared over 5x squared. And so what's my higher power? Are they the same, or is one bigger? They're the same. And so when they're the same, we do have a horizontal asymptote. And we'd have y equals our coefficients. And so our coefficients turn into what? 3 over 5. And so this function would have a horizontal asymptote at y equals 3/5. All right, let's look at B. And so what am I looking at the numerator? 2x. What am I looking at the denominator? An x squared. And so who wins? The denominator wins. So does it give a horizontal asymptote? Yes. What is it? Y equals 0. I don't want just the word or the number 0, because 0 is a number. Actually, this one's a null set. But like y equals something is a line. A horizontal asymptote is a line. And so we need y equals something or x equals something if we're going to form a line. In this case, we're going to talk about y's. All right, let's look at part C. And so what am I looking at on this one? 2x squared and 5x. So that's my in behavior model. That's what I care about. And so what do we know? Who won? The numerator won. So what do you know? It has an oblique or slant asymptote. All right. So no horizontal asymptote. It has a slant or an oblique asymptote. All right. I'd like you to do D, E. All right. Austin's going to help me out. Which one am I looking at? D. So we're at 4x and 8x. So does this one have a horizontal asymptote? Yes. And what would it be?
4 over 8
or 1/2. We can simplify it to 1/2. All right. Calling somebody. Robert, help me out. Does this one have a horizontal asymptote?
Yes.
Yes. What do we got?
Y equals 0.
Y equals 0. All right, because we got 3 over x squared, so that bottom wins. Pick somebody.
Lucas.
So the denominator wins. So not have a horizontal asymptote.
So the denominator wins, so we get y equals 0. All right. This 2x is on my denominator, and we have -4 in my numerator, so -4, 2x wins, we get y equals 0. Let's look at this. So now we're going to put limit statements on our in behavior, okay? And I want you to put a side note, okay, because I want you to get this definition of a horizontal asymptote. A horizontal asymptote is really a limit to infinity and a limit to negative infinity. That's truly what a horizontal asymptote is, all right? That's the definition I'm going to use in calculus. I do know that calculus teachers that you might have. And so that's what we use in calculus, and so that's what we might as well use here. All right, so that's what a horizontal asymptote is. It's an in behavior, which means it goes to infinity or negative infinity, all right, as x approaches them. All right, so let's look at part A now. All right, so now we're just going to put limit statements on this. So when I go left, how do I write my limit statement? My limit as x approaches what? Negative infinity of my function. And then as I go right, how do I write my limit statement? My limit as x approaches positive infinity of my function. So now let's talk about them. So it's just like what we did before, we just have different notation now. So what's my in behavior model on part A? What am I looking at? In my numerator, I'm looking at what? 2x cubed. What am I looking at in my denominator? 6x cubed. All right. So who won? They're the same power. So what do we look at? The leading coefficients. So what do we get? 1/3 or 2/6. All right. And so negative infinity and infinity are both going to be 1/3. It will play the same way. All right. So let's look at part B now. So when I go to the left, it's really a limit as x approaches negative infinity. And technically this is g of x. I've had students miss up that everybody writes f of x all the time. This one's notated g of x. And so this one would be a limit as x approaches positive infinity of g of x. So let's look for my in behavior model. So in my numerator, which one am I looking at? What is my leading term? 5x squared. In my denominator, what's my leading term? 2x cubed. Who won? Denominator 1. So what do we go to? It goes to 0. So my limit as x approaches negative infinity is 0, and my limit as x approaches infinity is also 0. All right? All right, let's do this next one. So when I go left, I say the limit as x approaches negative infinity of what this time? H of x. Good. And then my limit as x approaches infinity of h of x as I go to the right. Now, this one's slightly tricky, but let's talk about it. So, in my numerator, what's my leading term? Negative 3x to the fourth. What's my leading term on my denominator? An x cubed. What happened? It's a slant, right? And if I'm talking about a slant, it's either going to go up or it's going to go down, okay? It's not leveling off at a number or 0 this time. Is everybody following me on this? So my only two options is it goes to infinity or it goes to negative infinity, all right? It's going to do one of these two things, all right? And so now we have to figure out which one it is. And so when I substitute in negative infinity, if I substitute in a negative raised to the fourth power, is that positive or negative now? It's positive. And then I have a negative 3 times a positive, which is positive or negative? It's negative now. So it's negative 3 times a positive is negative, right? And then over negative infinity cubed. So a negative cubed is what? Negative. So I have a negative over a negative, which makes it what? Positive infinity. And so as x approaches negative infinity, h of x goes to infinity. And I'm gonna say this again. So as x decreases without bound, h of x increases without bound. All right, so we're going to do it again. So now we're going to basically substitute in infinity. All right, and so infinity to the fourth power is still positive infinity, yes? So then negative times a positive is a negative over a what? Positive. So I have a negative over a positive, which makes it what? Negative infinity. So this one goes to negative infinity. And this is how we read it. So as x increases without bound, h of x decreases without bound. So as I move right, it goes down. As I move left, it goes up. All right, pretty good? Cool, let's look at graphs now. All right. So these don't have names on them, so we're going to give them some names. D is going to be called A of X for Asher, and E is going to be C of X for Connell. All right, so there we go. Now we got names to our functions. So when I go to the left, I do a limit as x approaches negative infinity of A of X. And then if I go right, my limit as x approaches infinity of A of X. So what's my left-hand behavior? So as x approaches negative infinity, as it goes left, what's it go to? It doesn't go down. As it moves left, where is it going? It goes to what? What number is it leveling off to? It goes to 2. All right, it goes to 2 right there. All right, and then as x approaches infinity, as it moves to the right, what number is it going to? 2. All right, so now let's do the same thing for E. So as my limit, as x approaches negative infinity of C of X, and my limit as x approaches infinity to my right of C of X. All right, so as it moves left, where's it going? Negative 1. As it moves right, where's it going? Negative 1. All right, pretty good. All right, so now we're going to finish this up with slant asymptotes. All right, so what do you know to get a slant asymptote? The numerator has to be what? Exactly what? 1 greater than the denominator. All right, and when that happens, Robbie, all right, when that happens, f of x has a slant asymptote parallel to the line y equals a over bx. So it's the leading coefficients and then an x. I'd star that if I were you. All right, and so our slant asymptote is parallel to it. That is not actually the slant asymptote, but it's parallel to that line. Later on this year, we will get to the actual slant asymptote, but it requires long division. All right. All right, so let's look at this one. Robert's going to read for us.
I'm reading this slant asymptote.
Which?
Huh?
Which?
Okay. Which of the following rational functions has a slant asymptote parallel to the line y equals 1/2 x?
All right, so parallel to that line. All right, so let's look at number 1. So what am I looking at for this one? What term am I looking at in my numerator? X squared. What term am I looking at in my denominator? 2x squared. Does that give me a slant asymptote? No, it gives me a what? It gives me a horizontal asymptote at what? Y equals 1/2. Exactly. All right, let's look at number 2. So what am I looking at in my numerator? X squared. What am I looking at in my denominator? 2x cubed. Does that give me a slant asymptote? No, it also gives me a what? A horizontal asymptote. This time at what? Y equals 0. Let's look at number 3. What am I looking at in my numerator? What am I looking at in my denominator? 2x. Does that give me a slant asymptote? Yes. Why? Because the numerator is 1 bigger than the denominator. And so then we look at what? It's coefficients. So then it'd be parallel to y equals what? 1 over 2x. So did number 3 work out? Yes, let's look at number 4 now. And so what am I looking at in my numerator on number 4? An x to the 4th. What am I looking at in my denominator? A 2x squared. Does that give me a slant asymptote? No. Why not? It's not exactly 1 greater. All right. That's going to go to infinity or negative infinity, but it's not a slant asymptote on this one. All right. It's going to go faster. All right. And so the only one that worked out was number 3.